occurring. All right. So for this one, we're gonna have three formulas, but pretty much what we're gonna just go ahead and do, we're gonna use this formula over here. All right. So if you remember, we just went over the multiplication rule. So if you remember the multiplication rule, you're saying if I want to find the probability of event A and B occurring, all I have to do is get the probability of event A and multiply it by the probability of event B. So if the events are truly independent, this probability will be equal to the probability of the right-hand side. All right. Any question in regard to that so far? All righty then. So let's go ahead and do this very first problem. So if you look at this first problem, it says probability of n is equal to 0.8, probability of n is equal to 0.25, probability of r is equal to 0.6. So that's information they already gave us. So for part A, it says if the probability of m and n is equal to 0.20, so they're telling us probability of m and n is equal to 0.20. We want to find the event n and see if it's independent from event n. So what we're going to go ahead and do, we're going to go ahead and use this formula over here. So I already know the probability of A and B is equal to 0.20. So let me put like a little vertical line right here, separation. It'll put 20. So now what we want to do, we want to get the probability of A and multiply by probability of B, sorry. So what we're going to do, we're going to get the probability of n and multiply by the probability of n. So we're going to say probability of n multiplied by the probability of n. So if we look at the problem, they told us probability of n is equal to 0.8. So we'll put 0.8 here. If you look at the probability of n, it's 0.25. Any questions so far? I got 0.80 times 0.25. All right. So up to where you want to go ahead and do, you want to go ahead and do 0.8 times 0.25. So what's 0.8 times 0.25? Now, if you want, you could type it into the chat. For that way, I know you got your answer. So if you do 0.80 times 0.25, what do we get? You got 0.2. So you get 0.20. So if you look at this and this, they're equal to each other. So since both of them are equal to each other, we're going to say they're independent. So they're independent event because one event doesn't influence the probability of the second event. And if you look at it, whenever you get the left side and the right side equal to each other, that means they're independent event. All right, so that's the first example. Any question in regard to the first example? All right, so let's do part B. So for part B, all this changing, instead of us doing it for event M and N, now we're doing it for N and R. So they tell us the probability of N and R is 0.30. So I know the left side is equal to 0.30. And they're telling us we want event N and R. So what's the probability that event N occur? So in the problem, what do they tell us the probability of n is equal to? Yeah, 0.25. So we know probability of n is 0.25. What is the probability that r is occurring? Or what's the probability of r? Yeah, 0.6. So now I'm going to go ahead and multiply this out. So I'm going to say 0.25 times 0.6. Let's say 0.25 times 0.6. And if you multiply those two out, you get 0.15. So if you look at it, 0.30 is not equal to 0.15. So since they're not equal to each other, for this one, we'll say they're dependent. And that's it. All right. Any question in regard to the second problem? All right, so let's do this last one, and then we'll do the Bangs theorem. So for this one, we're gonna do with a two-way table. So what we want to see are the events of being a female and liking Game of Thrones independent. So if they are independent, that means that it doesn't matter, or like your gender has no influence on whether you'll like Game of Thrones or if you'll dislike Game of Thrones. If they're dependent mean that your gender should influence whether you're gonna like Game of Thrones or not like Game of Thrones. So for this one, we're gonna have to find. So we want to find if gender of female and liking Game of Thrones are these two events independent. So I'm gonna say female is equal to F. I'm gonna say liking Game of Thrones is L. So if I go back to this formula over here, that's the way I'm gonna set it up. So I'm gonna set it up the probability they're female and like Game of Thrones should be equal to the probability they're female multiplied by the probability they like Game of Thrones. So we're gonna find the probability they're female and like Game of Thrones should be equal to the probability of female multiply by the probability they like Game of Thrones. Right. So far, any question in regard to the notation? All right. So let's go ahead and let's find these individual probability. So first one, we're gonna find how many female like Game of Thrones. So usually for this, the easy way to do it is just kind of think about where do they intercept. So first, let's get how many females. So females are over here. So that's how many total females I have. Now what we want to see where are the people who like Game of Thrones. So like Game of Thrones will be over here. So where do they intercept? Which number do they intercept at? 60. So you put 60 over here. And you just divide it by the total. So in this one, if you look at it, there's a total of 123 people. Yeah. So that's it for the left side. So that's how you get the left-hand side. So now for the right-hand side, we're gonna get the individual probability. So right now we're gonna just find what percentage of people are female. So how many total female do we have in this study? Yeah, 90. Good, Valerie. So you have 90, and you divide this by, once again, the total. So 123. How many people do I have that like Game of Thrones? in this study? Yeah, 82. Good job, Karen. There you go. 82. And you divide this by 123. All right. All right. So far, everybody good. How I got 60 divided by 123 is equal to 90 divided by 123 times 82 divided by 123. All right, sweet. So up next, we're gonna go ahead and do just multiply this out and just simplify it. So first, I'm gonna do 60 divided by 123. So 60 divided by 123, you get 0.4878. All right, so that's my left-hand side. So the left-hand side is equal to 0.4878. So if the events are truly independent, the right-hand side should also add pretty much give me 0.4878. So now I'm going to do 90 oops, divided by 123. I'm going to multiply this by 82 divided by 123. All right. So once you do 90 divided by 123 times 82 divided by 123, what do you get? Do you multiply those out, Karen, though? Yes. Actually, here, let me show you on ClassCal. Should have that here. That we could say 90 divided by 123. Then we'll put this. Then we'll say multiplication. And then we'll say 82 divided by 123. And if you look right here, we get 0.4878. That's exactly what we got for the left-hand side. So let's go ahead and put that. So let me just put that 0.4878. So if you look at, we get the left-hand side to be 0.4878. We get the right-hand side to be 0.4878. So we could say the event of being female and liking So we'll say the event of being female and liking Game of Thrones are independent. Yeah, cool. All right. So the way that you get the 60, so just remember the 60 is how many females do we have that like Game of Thrones? Because that's what this part over here represents. It represents how many female do we have that like Game of Thrones. So here go, how many people do we have that like Game of Thrones? Here go, how many total females we have? So you just want to see where do they overlap. So they overlap at 60. So that's where the 60 come from. And then you just divide this by the total. And the total is right over here, the 123. All right, but that's it in regard to how to test to see if something is independent. Any question in regard to how to test to see if something is independent? All right, so up next, we're gonna go ahead and we're gonna do Bayes' theorem or Bayes' rule. So for this section, where we're gonna go over tree diagram, but we're also gonna go over Bayes' theorem or Bayes' rule in this case scenario. So you do want to use a tree diagram when you're doing Bayes' rule because it will help you out for this problem. All right, so here is the formula, but the thing is the formula is pretty like I'll go over how to do the formula, but I'll also go over how to do it just by using how you call it by using the tree diagram. So what we're gonna go ahead and do, we're gonna do part A. Part A, we're gonna do with the tree diagram. Part B, what we're gonna go ahead and do, we're gonna do that without the tree diagram. We'll do it with the formula, and that way, whichever way you like best, that's the way you're gonna do it for a test or for a quiz. So let's go ahead and do this first problem. It says a certain virus affect 1 in every 400 people. So it says a test used to detect the virus in a person is positive 85% of the time if the person has the virus, and 5% of the time if the person does not have the virus. This 5% result is called a false positive. Let V be the event the person has the virus, and let P be the event the person tests positive. All right. Any question in regard to that paragraph? Okay. All right. So one thing you kind of have to know, if we want to say the complement, what we're gonna do, we're gonna say whatever A is. If we want to find the complement, we're gonna put a bar over it. So that's the symbol that we're gonna use to represent the complement. So say if the event is that it rained, if I want the event is that it doesn't rain, here, give me a minute. It stopped sharing, so let me reshare. So say if we have the event that is rain, if we want to find the complement of the event, anytime we're finding the complement, we put a bar over it. And that just means that we're finding the complement. Going slow. Okay. So let's go ahead and do part A. So remember, part A, we're going to use a tree diagram to do this. So for part A, it says find the probability that a person has the virus given that they tested positive. So i.e. we're finding probability of V given P. All right. So right here, what's the given? What do we already know? Do we already know they have the virus or do we already know they tested positive? So do they have the virus or did they test positive? Cool. Perfect. Yeah. So they tested positive. So going back to last lecture, if you remember the conditional probability says we get probability of V and P and you divide it by the probability of the given, which is the probability of P. So that's what we're gonna find right now. So we're gonna find the probability of V and P, and then we're gonna divide that by the probability of P, which probability of P is probably they tested positive. Any question in regard to so far that formula? All right. So up next, we're gonna go ahead and do our tree diagram. So we're gonna do our tree diagram somewhere over here. So the tree diagram, we're gonna start off by doing 2 branches. So what come first, the virus or you getting tested? Like, which one do you think I should put first, virus or you getting tested? Okay, which one would you have first? So you'll have the virus first. So what we're gonna do, we're gonna say virus or no virus. And remember, that's why we put the bar over it, because the bar just means we have no virus. All right. Everybody good so far on V and V bar? Alrighty. So up next, we're gonna go ahead and we're gonna go ahead and now do, so you first get the virus or you don't have the virus, and then you get tested. So once you get tested, what are the 2 options that you could get when you get tested, that you test what? Cool. So you test positive or negative, but in this case scenario, we're not gonna say negative. So we're gonna say P, and we're gonna say P bar. Because P bar, remember, P bar is the complement. So if P represent positive, that means P bar represent negative. And we're gonna do exactly the same thing for actually. All right. Everybody goes so far on this tree diagram. Yeah. All right. So up next, what we're gonna go ahead and do, we're gonna go ahead and fill out the tree diagram. So right now we have the branches, but pretty much what we have to do now, we have to add the probability. So let's look at the probability somebody have the virus. So how many people, well, what percentage of people will have the virus? Or what fraction of people will have the virus? Well, that's actually how many people will test positive for the virus. But if you look at it, how many people do they say will have the virus? And cool, yeah. All right, good. So if you look at what Brando said, he said 1 in 400, and that's correct. Good. That's what they tell us right over here. They tell us a certain virus affect 1 in 400 people. So that's the probability that somebody will have the virus. 1 in every 400 people. So now what I want to do, I want to find out how many people won't have the virus. So if I know 1 out of 400 people will have the virus, how many people will not have the virus? So if I know 1 out of 400 people will have the virus, how many of those 400 people will not have the virus? That's 399. They put oops, sorry about that, using the highlighter. So you get 399 out of 400. Everybody got 140 divided by 399. Well, sorry. The 1 divided by 400 and the 399 divided by 400. Okay. So up next, what I'm going to go ahead and do, we're going to try to find this probability over here. So to find that probability, you have to pay attention to the branch. So for this branch, we already know these people have the virus. So I want to find out, of the people who have the virus, how many of them will test positive? So of the people who actually have the virus, what percentage of them will test positive? So how many people who have the virus will test positive in this case scenario? Well, let's look at the second sentence. So if we look at the second sentence, it says a test used to detect the virus in a person is positive 85% of the time if the person has the virus. So that's telling me if the person has the virus, they test positive 85% of the time. So we'll put 0.85 there. So if I know 85% of them test positive, what percentage of them test negative if they have the virus? Yeah, 0.15. Good, Junior. They put 0.15 there. All right, and that's it for that branch. So now what we're going to go ahead and do, we're going to go ahead and focus on people who don't have the virus. So of the people who don't have the virus, how many of them test positive? So of people who don't have the virus, how many of them test positive? And if you want to keep on reading where I highlighted blue. Like if you look at the "and" part, that should give you the answer for the next portion. So what percentage of people who don't have the virus test positive? Well, if you look at this portion over here, it says 5% of the time if the person does not have the virus, they'll test positive. So right here, we'll put 0.05, and below here, we'll put 0.95. Because the 0.05 represent how many people will test positive, the 0.95 will represent people who test negative. All right. Any question in regard to how we got those branches? All right. So what we're gonna go ahead and do, we're gonna go ahead and multiply these branches. So I want to get the, well, here, let's use black. So I want to see what percentage do the branches give me. So the first one I want to do this branch. So we're going to do the first branch. So to do that, we're going to do 0.85 multiplied by 1 divided by 400. So I'm going to say 0.85 times 1 divided by 400. And you get 0.002125. All right, so that's that first branch. Now what I want to do, I want to get the second branch. So I'm going to get, they have a virus, but they tested negative now. So now you're going to do 0.15 times 1 out of 400. So say 0.15 times 1 out of 400. And you should get 0.000375. Any question in regard to those two probability? All right. So up next, we're gonna go ahead and do this next branch. So the next branch is people who don't have the virus, but they tested positive. So to find that probability, we're gonna get 399 over 400 multiplied by 0.05. So we'll say 399 divided by 400 times 0.05. And you get 0.049875. All right. So the last one we're going to do, we're going to focus on people who have the virus and tested negative. So for that one, we're going to say 399 divided by 400 times 0.95. So let's see what that gives us. So 399 divided by 400 times 0.95. You get 0.947625. All right, so we have all of our probability. So we're going to use these probability to now find our answer. Any question in regard to how I got these four probability? Okay, so I'm going to color coordinate these probability. So we'll say this is yellow, this is blue, this is green, and we'll do red. So let's go back to the conditional probability that we first did. So if we look at the top, it says probably somebody had the virus and tested positive. If I look at my four options over here, which of these four options give me the probability that they have the virus and tested positive? Would it be the yellow one, the blue one, the green one, or the red one? Yeah, so it'll be the yellow. So on top, we'll put the yellow one, which is 0.002125. All right, so that's which one you put on top. Any question on why we chose that one to go on top?
Wait, why did you choose that to go on top?
All right, so you see how, you see how this one is V and P? So V mean they have the virus and P mean they tested positive, correct? So if I want a person who had the virus and also tested positive, well, if you look right here, here are the people who have the virus. Here are the people who tested positive. So that means I want to use this branch right here. So if I use that branch, I have to do 0.85 times 1 divided by 400. So that means we use this probability over here, because if you do 0.85 divided by 1 divided by 400, it give you that value. So that's why we're using that branch, because we want people who tested positive and had the virus.
Okay.
So let's do the bottom. So if you look at the bottom says probability tested positive. So of these options over here, where I'm drawing my arrows, how many of them tested positive? So of these number, there's multiple options that they tested positive. So which color should I use if I want to test it positive? Well, which color corresponds to that one, Brando? Well, let's look at the branches. Let me kind of clean this up a little bit. So if I look at this one over here, did that one give me a positive? Because if you look at the branch that I highlighted is people who have the virus and tested positive. So did they give me a positive test result? So yes or no? Cool. So since it does give me a positive test result, that means we're gonna use this probability. But the thing is, that's not the only one that will give us a positive test result. So let's continue looking for more positive test results. So let's say a person had the virus but tested negative. Did that give me a positive test result?
No.
No. So that means we're not going to use this one. So let's go on and let's see this one. So say the person doesn't have the virus, but they tested positive. Should I use that result? Well, if you look at it, since they tested positive, you want to use that test result. So I'm using this number over here. And then finally, we have this one where a person will not have the virus and they test negative for the virus. So in this case scenario, we're not going to be using this probability. So the two probabilities that we're going to be using because we want a positive test result are going to be the yellow probability, but also the green probability. Any question why we're using the yellow and the green one for test positive?
Sorry, could you go over that again? Like why? Not
Well,
everything, just like why.
well, so we want it to be a positive test result. So we're just looking to see which one gave us a positive test result. So if you look at this one gave me a positive test result. This one also gave me a positive test result. So that's why I'm using the green one, and that one I'm using the yellow one. So if it gave me a positive test result, that means I'm going to use that entire branch. Does that kind of make sense?
Hmm.
Okay. So that means I'm gonna get the yellow probability and I'm gonna add it to the green probability. So we're gonna say 0.002125, and we're gonna add it to 0.049875. So let me go ahead and add this. There you go, 0.002125 added to 0.049875. So if I add these two numbers together, you will actually get 0.052. So now what you want to do is get this number over here and divide it by 0.052, and then that'll be your answer. So you get 0.002125 divided by 0.052, and you get 0.04. What is it? 4%. And that's your answer for A. Any question for A? All right, so that's using the tree diagram. So up next, I'm going to show you how to do it without using the tree diagram. And we're not going to do B. We're going to do A again. So we're going to say probability of V and P. So we're going to find the probability somebody had the virus given they tested positive. So in this case scenario, we're going to go ahead and use the formula. So we're going to use this formula on top. So we're going to say probability of V. Then we're going to multiply this by the probability of P given A, or sorry, given B. And then we're going to say divided by the probability they have the virus. And we're going to multiply that by the probability that they tested positive given they have the virus. And then we're going to add this to the probability they don't have the virus and tested positive given they don't have the virus. So if you do want to use a formula, the best thing you want to go ahead and do is just make all of the notations. So let's go ahead and just start doing notation. So let's find the probability of V. So the probability of V is the probability that they have the virus. So the probability that they have the virus is just 1 divided by 400. So that's the probability that they have the virus. Up next, what we have to go ahead and do is find the probability that they don't have the virus. So if I know 1 out of 400 people have the virus, the probability that they don't have the virus is 399 divided by 400. So far, everybody good with those two notations? So far, we found these probability over here. So right now, what I want to go ahead and do, I want to find the probability somebody would test positive given they have the virus. So we want to find how many people test positive when they have the virus. So what percentage of people will test positive if they have the virus in this case scenario?
The
So
0.85, right?
yeah, the 0.85. Good, Adam. So you say 0.85 here. All right, so that's this probability, and that's this probability over here. So the last probability we're going to go ahead and find is the probability they test positive given they don't have the virus. So how many people will test positive given they don't have the virus? Yeah, 0.05. So 0.05. So all we have to go ahead and do is substitute everything in. So right here we said probability of V. You do 1 divided by 400. Once again, right here we said probability of V. You put 1 divided by 400. Right here where it said not V, that will be 399 divided by 400. Right here where it says probability of V given P given V, it will be 0.85. For this one, it will be 0.85 also. And then this one will be 0.05. So if you actually go ahead and just work all of those little fractions out, you should get the same probability of roughly 0.04. And that's how you do it using the formula. Any question in regard to how to do it with the formula? Yeah. So which one do you like better, the formula or the tree diagram? So the tree diagram with the first one, the formula was the one that we just did right now. So you can either put it in the chat, or if you like neither, put neither.
Bro, I wish neither.
All right, so most of you said formula, so I'll continue on. Will you do the formula then? So let's do the next one to let you get some more practice. So let's go ahead and do this one. So it says anatomy of a test. So it says cancer testing scenario. So it says 1% of women have breast cancer. 80% of mammograms detect breast cancer when it is there. 9.6% of mammograms detect breast cancer when it's not there. Now, suppose you get a positive test result. What are the chances you have cancer? Okay, so let's look at the last. Well, let's look at the first line where it says 1% of women have breast cancer. So we'll say probability somebody has, we'll say breast cancer, so we'll say BC. So what's the probability somebody has breast cancer or a woman have breast cancer? So remember, you can just type it into the chat room. Yeah, 1%. So we'll say 0.01. What would be the complement of that? So say if I want to find the probability somebody doesn't have breast cancer, what would be the probability somebody doesn't have breast cancer? Cool. Thanks, Karen. 0.99. All right. So we're all done with this first one. So let's do the 80%. So it says 80% of mammograms detect breast cancer when it is there. So that's telling me the probability. We'll do a different color. So the probability somebody have breast cancer. Oh, sorry. So this is telling me the probability you get a positive test result given that you have breast cancer. So that would be 0.80. So that what the second line telling us, it's telling you 80% of mammogram detect breast cancer when it is there. So telling us we do have breast cancer, and this is the percentage of the time you'll get a positive test result. Any question in regard to why we put probably a positive given BC? All right, so let's do the 9.6. So the 9.6, what does the 9.6 represent? Well, the 9.6 represents the probability somebody tests positive. But in this case, do they have breast cancer? No. So right here we'll put BC, but we'll put BC with the horizontal line or with the bar to notify that they don't have breast cancer. So far, everybody good? Or, well, let me actually put the percentage. Everybody good with those 3% represent or 4% represent? Okay, so let's go ahead and do the question. So it said, now suppose you get a positive test result. So they're telling us we got a positive test result. So that's the given. So we know we got a positive test result. So if we got a positive test result, it said, what are the chances you have cancer? So we want to know what are the chances you have breast cancer. So we'll put B, C here. Okay. Any question where you have BC given positive? All right, so let me go back and look at the formula. So that's the formula we're going to use. So if you look right here, it says probability of A. A is whatever we have in front. So we say probability they have breast cancer. If you look at this, now we have probability of B given A. So B is what's given. So we're going to say probability they test positive given they have breast cancer. So that's what we want to put on top. Any questions so far? I got the top. All right, so let's do the bottom. So if you actually look at the formula, this portion and this portion is always the same. So we're going to put probability they have breast cancer times the probability they test positive given they have breast cancer. So let's do this part now. So if you look at it, it has A, which A is the front one. So in this case, it's breast cancer. So in this case scenario, we're going to say they don't have breast cancer. Okay, we're going to put BC with a bar. Okay, if you look at it, it has a bar right here. And then if you look at this one, it says probably a B given A, but A is the bar. So we're going to say probability they test positive given that they don't have breast cancer. All right. So that's going to be the formula that we're going to be using. Any question in regard to that formula? All right, so let me go ahead and erase this. All right. So far, I'm going to go ahead and just do this probability because that's 0.01. So we're going to say 0.01, and then you say 0.01. Then we go ahead and find this probability. What's the probability that they test positive given they have breast cancer? What did we found that to be? So what's the probability they test positive given they have breast cancer? Yeah, 0.80, good. So you put 0.80 here. You put 0.80, oops, put 0.88 by mistake, 0.80 here. All right, so we got these two over here. Now what we have to do, we have to find these last two probability. So we want to find the probability that they don't have breast cancer. So what percentage of people don't have, or what percentage of women don't have breast cancer? Yeah, 0.99. And what's the probability of people who test positive given they don't have breast cancer? Yeah,
1.
0.096.
Oh, sorry.
You're good, Anna. All right. Everybody good how I got all of these numbers so far? Okay, so I'm going to switch over to class calc and we're going to do all of this all at once so that we could get an answer. All right, so the first thing you want to do, you want to do the fraction. So on top, we're going to put 0.01. We're going to multiply this by 0.80. Then the bottom, we're going to put 0.01, multiply by 0.80 again. But now we're going to add it to 0.99, multiply by 0.096. And if you look at the answer that we get 0.0776, or if you want, you could say 7.8%. And that'll be your answer for the last problem. Any question in regard to the last problem? All right, so let's do this last one, and then that'll be it for today. So for this one says 1%. Oh, here, let's give cancer a break. Here, let's do the one about the manufacturing boats. So it says in a factory, there are two machine manufacturing boats. The first machine manufactures 75% of the boats, and the second machine manufactures the remaining 25% of the boats. From the first machine, 5% of the boats are defective, and from the second machine, 8% of the boats are defective. A boat is selected at random. What is the probability that the boat came from the first machine, given that it is defective? Okay. So if you kind of notice for this one, they're talking about manufacturing. So how much does a machine manufacture? And then they're talking about how many of those both that are manufactured, how many of them are defective. So what we're gonna go ahead and do, we're gonna say, so we're gonna have machine number one, and then we're gonna have machine. Well, here, let's just make this simpler. So we'll have the first machine, which is just M, and then not the first machine, which will be M bar. All right. So what percentage of the both were produced by the first machine?
75.
75. So right here, we'll put 0.75. So what percentage of the both was not produced by the first machine?
25.
25, good. All right. Everybody good with that so far?
Yep.
All right. So let's go ahead and do the 5%. So the 5% represent the first machine. So it says from the first machine, 5% of the both are defective. They're telling us, so we're gonna say that. So we're gonna say probability the defective given they came from the first machine is 5%. So we'll put 0.05. So then we have the probability it's defective given it came from the second machine. So we'll put a bar right here. What percentage should that be? Well, for this one, it will be the 8%. Because for Brando, the 0.95 represent how many of them are not defective. But for this one, we don't want it to be defective. We just want it to come from the second machine. All right. Any question in regard to those four probability? All right. So let's go ahead and find what they're see what they're asking us to find. So if you look at it, said what is the probability that the boat came from machine one, given that it is defective? So right here, the given is that it's defective. So we're gonna say probability it came from machine one. So machine one given is defective. So let's go ahead and write this out. So I'm gonna go ahead and just get the formula again. All right. So if you look at probability of A is the first one. So we're gonna say probability of M. If you look at the second one, it's saying probability of B of A. So that's gonna be probability defective given it came from machine one. And you divide this by pretty much the same thing. Probability it came from machine one times the probability is defective given it came from machine one. Then what you want to do is add it to this portion, which is essentially this. The only thing they're going to change, you're going to put a bar. So we're going to say probability came from the second machine times the probability is defective given it came from the second machine. So that's how we're going to use the formula. So if you look at it, we already have all of those probability. So the probability of n will be 0.75. This probability over here is 0.05. So you get 0.05 all divided by exactly the same thing, 0.75 times 0.05. And then you add it to the probability it came from the second machine, which we found it to be 0.25, multiplied by the probability it defected given it came from the second machine, which is 0.08. Any questions so far on why we substitute any of those numbers in? All right, so the last part we're going to use class calc, and then that will be it for that problem. So for this one, first you want to do the fraction. So let's say 0.75 multiply by 0.05. And then we'll say 0.75 times 0.05 plus 0.25 times 0.08. If you look at that, you get 0.6522. So if you look at that, so that will be our answer for the last question.
The 0.652?
Yeah, the 0.652. The one that came from class calc. So that will be our answer. All right, and that's it for that one. Any question in regard to the last problem? All right. So pretty much that's it for today's lecture. So I'll see everybody on, what was that, Thursday? If you have any question, I am going to be holding office hours. So if you do have any question, just go